Welcome everybody to today's morning's CQT talk. Thank you all for coming, and a very warm welcome to the online audience as well. The talk today is being presented by Goutam Paul, who is an associate professor and head at the Cryptology and Security Research Unit in the Indian Statistical Institute, Kolkata. And he'll be speaking on monogamy of entanglement and its violation in indistinguishable particles. He has been working in the area of cryptology for some time, and he has also started working and exploring research areas in the field of quantum information and quantum computing. So I welcome Professor Paul to deliver his talk.
Thank you, Anindo and Alex, for hosting me and giving me an opportunity to present one of our recent results here. So, good morning, everyone, for coming to attend the talk. So, as you see, it's monogamy of entanglement and its violation in indistinguishable particles, right? So, all of us know that monogamy cannot be violated. It's kind of a fundamental principle, right? But here we show that that holds restricted to the distinguishable setting. And in some view of indistinguishable particles, that is not necessarily true. So that is the main result which we are hinting at. So we are not actually contradicting the main monogamy result that has been there, right? So it's a fundamental result. All we are saying that maybe implicitly in the proof assumption, it is assumed that they apply to distinguishable particles. So that is the thing. Okay, so this is based on our recent paper last year, which was accepted in PRA as a letter. Okay, and one thing is important I want to highlight in the title of the paper, that this violation of monogamy, because you know that that is we have several measures of monogamy, right? So certain measures are monogamous and certain measures are non-monogamous, like for the same dimension, for the same setting scenario. So when we say that monogamy is violated, obviously we mean that it is violated by the same measure that would be monogamous for the corresponding distinguishable particles, so that the comparison is even, right? So we know that if we change the measure, that it could change the property, but here we keep the same measure and the same dimension. So this is the overview of my talk. First, we'll talk about indistinguishable particles with multiple DoFs, then monogamy of entanglement, distinguishable and indistinguishable setting, then our contribution, DoF trace out rule, and maximum violation of monogamy, followed by discussion. Okay, so yesterday, I think Shoma already presented indistinguishable particles, but there he presented the particle view. So here it is the same thing with the DoF view. So you see that the wave functions of two particles A and B are separated. In region S1 and S2, there is no overlap. And in region S3, in diagram B, they are having overlap, right? So when they are in S3, we cannot say that whether it is which one is particle A or particle B. Now with the more degree of freedom, it becomes complicated, because now if you take the degree of freedom 1, right? So whether that belongs to particle A or particle B, you do not know. Similarly, degree of freedom 2, also whether that belongs to particle A or particle B, you do not know. So the indistinguishability happens at the degree of freedom level also. Of course, the 2 degrees of freedom are always distinguishable, because you have different measurement settings, right? Different devices to operate on them. But the same degree of freedom of 2 particles, they become indistinguishable, right? So that granularity we have to keep in mind here. Okay, so yes, so monogamy is a well-known thing in the quantum particle domain. Like if 2 particles are maximally entangled, then none of them can share any correlation, not even classical correlation, right, with any third particle. So that's what we mean. Right, so this is shown here. So E here, the math script E stands for any entanglement measure. So this A vertical, B means the entanglement measure between 2 subsystems which are on the 2 sides of the vertical bar, and rho is the density matrix. So this entanglement measure between A and B plus the entanglement measure between A and C, that is less than equal to entanglement measure between A and the subsystem BC taken together. So that's the quantitative view of monogamy of entanglement. Of course, maximum violation occurs when both the left-hand side quantities attain their maximum value, which we'll talk about in the next slide. And many of us know that there are several interesting applications of monogamy of entanglement. For example, if you want to prove security of quantum key distributions, especially entanglement-based protocol. Even if it is not entanglement-based, like for example, you can show BB84, which is non-entanglement based. It is equivalent to Eckart protocol, and then you can stretch the security proof down there, right? Then classification of quantum states, condensed matter physics, black hole physics, right? We all know that this the black hole information loss paradox, we will have a lot of interpretations using monogamy of entanglement. Right? Especially Susskind's work are important in this domain. So yeah, so the question is, does monogamy always hold? So before going to indistinguishable particle, even in the distinguishable setting, we know that it does not always necessarily hold. So it depends on two properties. One is the dimension of the particle, and second is entanglement measure, right? So for example, in Q-treats, using squared concurrence, that is the most common monogamy measure, it has been shown that monogamy is violated. So this is an example of Q-treat state, right? So 1, 2, and 3, these are the eigenstates. And we can show that here, if you calculate squared concurrence using the standard definition, C squared AB plus C squared AC will be 2, which is greater than equal to 4 by 3, that is C squared A given BC. So it violates. But if you are using squashed entanglement measure, then it obeys in the Q-treat, right? The same state. And if you come to qubit, then there are some measures which are known to be monogamous, like square concurrence, log negativity, entanglement of formation, Chalice entropy, etc. There are a lot of them, right? So this Q-treat versus qubit difference is important because the dimension is different. And also the Q-treat, we saw that two measures, one holds and the one does not hold, whereas in qubit, both the measures hold, right? So again, when monogamy violation, the definition of monogamy violation does not depend on whether violation actually occurs in nature or not, right? So we can always define, if this happens, then it is violated. So the definition is independent of the existence. So if Emax is the maximum value of the entanglement measure that is attainable by the function E, then by non-maximal violation, what we mean, because our paper is on maximum violation, right? So non-maximum violation means the individual measures on the subsystem A versus B and the subsystem A versus C, those are not maximum. So they are less than maximum. So they are not maximal, not necessarily maximally entangled, AB and AC. But if we add their entanglement measure, then that is greater than the maximum possible. It is possible. So for example, if the maximum is 1, you can have states where, here you have 0.6, here you have 0.5, and then it may be greater than 1, right? So under certain conditions, it is possible. And maximum violation is something where both the things, AB is maximum, AC is maximum, and that is always violation because, the sum is 2 into Emax, that is definitely exceeding Emax, right? So that is maximum violation. And we know that when we state qualitatively the monogamy result, that's what we mean, that A and B are maximally entangled, so they cannot be having any correlation with any other third particle, right? So basically focus on that. We don't focus so much on non-maximum violation, right? Okay, so cloning is another property of quantum state. If you know the state, you can clone it, of course, but if it is an unknown state, the no cloning theorem guarantees that you cannot have a copy, right? And it follows from the unitary linear transformation on the state, right? So it does not assume, cloning does not assume whether the states are distinguishable or indistinguishable. So that's what I want to highlight because we are going to use this result, right? No cloning theorem is kind of more fundamental because they do not, the proof at least uses linear algebra, linearity of quantum mechanics and stuff like that. And application is, of course, quantum error correction, cryptography, black hole physics, etc. So first of all, in distinguishable setting, maximum violation of monogamy imply cloning, right? It's easy to show. So on the left-hand side, by dotted diagram, we show maximum entanglement. So A and B share maximum entanglement, and A and C are maximally entangled. So we have an unknown state phi x, and the joint state of ABC is psi ABC. So we do a Bell state measurement on phi x and A. The output is y, and depending on the output y, as a function of y, we have a unitary transformation on B and C, the same unitary transformation, and that will create a copy of the state phi at B and C. So it will have two copies of the unknown state. Now, so the way we can argue is that maximum violation of monogamy is impossible in distinguishable setting. We can show that this phi B and phi C, these two copies, that is not possible because phi x was unknown. So the independent proof using linearity shows that such kind of system cannot exist. So therefore, the starting assumption must be wrong. So A, B, and AC cannot be maximally entangled, right? So that is the simple view on why monogamy violation cannot occur on distinguishable setting, right? Now, interestingly, there are scenarios where apparent maximum violation occurs. So consider three particles like B, A, and C, and each with 2 degrees of freedom, labeled by 1 and 2. So the first degree of freedom, A and B are maximally entangled, and in the second degree of freedom, A and C are maximally entangled, right? So I think it's A1, B1 should be there. So A1, C1 is wrong in the diagram. So A1, E, A1, B1, E, A2, C2, right? So now if you add them, definitely it violates monogamy of entanglement. So this type of state was proposed in many literature. So this is one of our works, so I'm citing it, but of course it's very common. And yesterday it was discussed that these type of states are called hyperentanglement. Okay, so what we say, I mean, it is not a contribution, but this is kind of another way of looking at it. I mean, it is obviously assumed when people talk about monogamy at the particle level, they kind of implicitly assume that they are working with a single degree of freedom. So either particles with single degree of freedom, or maybe particles having multiple degree of freedom, but we ignore the other degrees. We focus only on 1 degree of freedom. So that is kind of implicitly obvious assumption, which naturally people do not care to mention. But what happens if you do not make it explicit, then this kind of scenarios can occur, and then we can say, yes, A and B are maximally entangled, A and C are also maximally entangled, but then, right, equation wise, it's violating the monogamy, right? But so we just say that the equation needs to be rewritten. So it is nothing new or novel. It is just a rewriting, right? So it's in the introduction of our paper. So monogamy inequality using degree of freedom should be written something like this. So suppose we are talking about there could be multiple DoFs. So we can have the ith DoF of particle A, jth DoF of particle B, and kth DoF of particle C. So if we make that explicit, then we can write the entanglement between AI Bj and then AI Ck, and then between AI versus Bj and Ck, right? So if we make it explicit, then in that kind of scenario, this picture does not show violation, right? Because here the indices change, right? It's not the same AI, Bj, and Ck, right? So the A is not common, right? AI1, AI2, so it is different. You can see that if I had A1 in both the setting, right? A1, B1, and A1, C2, then it would have been a violation of monogamy. So the index of I should be same as in this equation. It's all AI, AI, AI. But if we change the index, as in this equation, this AI1 and AI2, right? So then, of course, it does not fall under this equation, and therefore the violation is not there, right? So particle view is kind of, I would not say it is a wrong view, but the particle view assumes we are talking about single DoF. So the particle view and the single DoF view are equivalent, right? So a more general way of writing the equation is the DoF version, which we have written here. Then it is kind of more proper, I would say. Yes.
How can we understand this degree of freedom? For example, if I have A and I have a momentum state and a internal state, that can be 2 degrees of freedom. Is that true?
Yeah, so I mean, degrees of freedoms are like, for example, polarization is 1 degree of freedom, spin is 1 degree of freedom, path can be another degree of freedom. So,
and then
so which you can independently measure.
I see. And what if A is a bipartite system, and then each party has a piece of state? That also works, right?
Yes. So yeah. So I should have said that this A, B, and C, these designations are not only particles. You can extend it to systems also.
All right.
Yeah, definitely. But when you talk about systems, then distinguishable and indistinguishable will have different meanings. So if we say 2 systems are indistinguishable, then each constituent inside the system also should be indistinguishable, right? So like that, corresponding, okay. Right? Yes. So this is one representation of indistinguishable particle, right? So 2 indistinguishable particles, each having DOF, are associated with spatial levels alpha and beta, and the ith and the jth DOF are represented by AI and BJ, right? Then the state can be written something like this. So the 2 with bracket denotes that it is a indistinguishable setting. Now, the density matrix can be written just from the Psi. Now, these kind of notations were proposed by Lo Franco in 2018 PRL, and in 2000, but they did not show how it is related to second quantization. They just showed that in the second quantization notation, there are some limitations. Some states cannot be expressed efficiently. With this notation, it can be expressed. That was their proposal. Whereas in 2019, this PRA paper, Lorenko proved that actually there is an equivalence between second quantization and this notation. So people can use any one. The only thing is that sometimes in second quantization, it becomes very tedious. The calculations becomes very complicated, and it's prone to error if you do with a lot of systems. Whereas if you work with this kind of notations, it makes somehow life easier. And they have shown like 2 different calculations, how they arrive at the same result. And of course, they prove the general result also. These are equivalent. So we are using this notation, this 2000 based on the 2019 result, that this is equivalent, because that makes our life easier. And so I'm not going into the details. So one of our main results before we show the actual monogamy violation is the DOF trace out rule, because when it is distinguishable particle, right? So if you have multiple DOF system or maybe multi-particle system, so if you want to measure a subsystem, you want to trace out the other guys, right? So that is pretty obvious. You just do the normal trace out operation using matrices. But here what happens in indistinguishable setting, right? If I say that I want to trace out the second degree of freedom, right? So now the question is from which particle, between which particle. So that becomes a complicated thing, right? So if I want to measure only the correlation between the first degree of freedom between 2 particles, right? But you do not know which one is A, which one is B. So the equations are little different. So that is, we show that it is non-trivial, and we propose a DOF trace out rule, and we show that our proposed rule is actually a generalized rule, because in the special setting, if we give labels to the particles, then the long calculation actually reduces to the distinguishable setting. So it covers the distinguishable trace out operation, which is obvious, but the indistinguishable, which is not obvious, it extends that. Okay. So with that, because if you have to measure subsystem entanglement, you need mathematically, at least you need to do the trace out. In experimental lab, it is quite easy because you just do not observe those degrees of freedom. Whatever you want to observe, you do your measurement of it. So of course, in indistinguishable setting, there may be challenge in experiment, right? Which I'm not aware of, but at least for distinguishable setting, if you want to do trace out operation, operationally in laboratory, it is a very trivial thing, right? You don't have to do basically anything. You just observe 2 particular degrees of freedom. But mathematical representation indistinguishability is a really tedious thing. Okay, so the main result is in qubit systems. We are very particular about our result. It is not in any dimension. In qubit system, indistinguishability is a necessary condition for maximum violation of monogamy of entanglement by the same measures that are monogamous for distinguishable particle. Now, why we have made a claim like this? This necessary criterion I want to highlight here, because it does not say that any arbitrary indistinguishable states, if you create, that will have maximum violation of monogamy. It does not say that. It only says that certain indistinguishable states you can create, which will violate the maximum monogamy. Distinguishable setting, there are no states which will violate monogamy, right? That is clear because of connection to no cloning. In distinguishable, it is not possible at all. But in indistinguishable setting, it is possible, but it is not universally possible. It's not any arbitrary random indistinguishable state if you give and if you claim it violates monogamy, that is wrong. We are not saying, right? It is possible to create structures. It is possible to create states which will violate. So it is existential proof that yes, violation exists. So that's why we say it is a necessary criteria. It's not sufficient, because if we say it is sufficient condition, then that means any arbitrary indistinguishable will have that. So our proof is not considering any arbitrary indistinguishable state. We demonstrate, we show existence of certain state. And that is actually related to what yesterday Shomo said, particle exchange, again, the same setting. So use particle exchange, and then we augment with certain, other tricks to show that this HHES kind of state, this hyper-hybrid entangled state that was proposed yesterday, that you have entanglement between same degree of freedom and the cross degree of freedom also. So that kind of state is possible to create using particle exchange paradigm in indistinguishable setting. And then using that, we can use the representation of such a circuit, like the state can be written as psi. Then you have do the, using the trace out rule, if you do the concurrence measure, then you can show that the monogamy is violated. So both the same degree of freedom link and the cross degree of freedom link have concurrence 1. Okay, so the open question. So which one is more fundamental, right? So no cloning theorem or monogamy of entanglement. Now I have seen some papers in PRA and PRL itself, which they have started in general introduction that no cloning and monogamy are equivalent, right? So what, in our view, when we say no cloning and monogamy are equivalent, that means monogamy will imply no cloning and no cloning will imply monogamy, right? So the result will be directed in both. So possibly that is true only in distinguishable setting, right? So people have that kind of indistinguishable setting. So people have that implicit assumption. But here we show in indistinguishable setting that does not work, okay? Because no cloning is more fundamental. The proof does not assume distinguishability or indistinguishability. It uses linearity of quantum mechanics. Whereas monogamy is not that fundamental, because in indistinguishable setting, it is violated, right? So one can ask the question that why the same kind of proof that if monogamy is violated in indistinguishable setting, why it would not lead to cloning, right? And that relates to the yesterday's discussion on unit fidelity quantum teleportation, right? So this unit fidelity quantum teleportation is not possible using indistinguishable particle. You see that this part of the circuit works like teleportation, right? Teleportation circuit. So for distinguishable, it is possible. For indistinguishable, it's not possible. So that kind of prevents the cloning to happen here, right? Using the same logic. So yeah, it's not a kind of a proof, but it is kind of an intuition why it should not hold in the indistinguishable setting. So that's one thing. So the claim is no cloning is more fundamental than monogamy, right? And another open question is the application of maximum violation of monogamy, right? So we know there are the monogamy result holds. We have a lot of application of that. For example, proving security of quantum key distribution. That is one obvious result, and that is a practical application. Of course, we don't have to go to black hole information paradox, that much abstract stuff. It's practically we have some application. But now, once we have the violation of monogamy, we were actually trying to do some crypto attacks or attacks on quantum crypto system using this. Like we are thinking, if let's say the attacker does some kind of indistinguishable states, right? So does it make the system vulnerable? Or if Alice and Bob uses indistinguishable states, does it make the system more secure? So that kind of things we're trying to analyze. So this is ongoing work, but it's still open whether maximum violation of monogamy can be practically useful, either from the designer's point of view, making it more secure, or from the attacker's point of view. Either way is fine as long as we have an application. So that is one open area after this theoretical question. And third is the violation possible for other quantum correlation like steering, coherence, discord? Like we talked about entanglement only, because that's kind of the immediate thing that comes to your mind when you talk about monogamy. But definitely these other things are worth looking at. Okay, so I will stop here. And so this is a brief overview of our group. I have currently 2 postdocs who are leaving actually, so I have positions if anyone is interested. Currently 6 PhD students. Shomo is one of them. He's graduating next month. He's defending his thesis. So there are other 4 students also will be leaving soon. So 1 will be remaining. And my research work originally was classical cryptography, but over last 5-6 years, I have moved into quantum information communication domain. So in quantum cryptography, I have some work on theoretical analysis of optimal attacks on BB84 crypto system. Okay, BB84 like crypto system. So by optimal attack, I mean, so any kind of attack that that an adversary does on a BB84 like setting, like it has to it has to introduce some noise in the system, even if it is not of preparation, measure and recent type of attack. It may have that the attacker has some ancillary state, make some unitary interaction with the ongoing particles and let it go, does not do any measurement, just do some unitary interaction. And then after the protocol is over, do some offline computation on the ancillary qubits. Right? So that's kind of the most general setting of an attack. So there the challenge is that the attacker wants maximum information gain from the system, right? So the information gain between Alice and Eve should be maximum, subject to the disturbance would be within the threshold, so that Alice and Bob cannot detect the presence of adversary. Like to them, the presence of noise and presence of adversary is indistinguishable. They will just estimate the channel noise. If it is above the threshold, they will abort the protocol, right? If it is below the noise, then below the threshold, they will run error correcting codes, then it will work fine. So that is the standard setting. Now, so here attacker's goal is to be within that limit, but still extract some information. And the Alice and Bob, their goal is to design the scheme in such a way that any disturbance, a minimal disturbance will, a minimal interaction will increase the noise to a large extent, right? So in that trade-off, from the attacker's point of view, we kind of show that if we make the noise a parameter, because for the attacker knows what is the current channel noise. An attacker knows what is the threshold that Alice and Bob can tolerate, right? Without the attacker being detected. So attacker knows the delta, if there is any gap between the current channel noise and the allowable threshold. So now the attacker can set, okay, I'm going to introduce this much noise, say D, right? So that the current noise and the D added is below the threshold. Now, given that noise, what is the maximum amount of information I can get about the secret key, like how many key bits and or any other information? So that's kind of an optimization problem. And one of our work is in that. That was also published in PR a few years back. And basically there we show that this kind of optimal attacks, there are many infinitely ways you can do the attack. So I think 20 years back, Chris Fuchs had a paper where he showed that such kind of attacks are possible using 2 specific ways. And he left the question open whether there are any other interactions or other ways of performing the attack. Right? So then we kind of generalize it and we show that there are infinite class of unitaries of performing the attack, of which like the Fuchs, these 2 specifics are just 2 instances of this infinite class. So that is the work on quantum cryptography mainly. Well, the work that was presented yesterday and today, they relate to quantum information. And in quantum communication, I have one PhD student who works in the quantum communication protocols, like for example, quantum secure direct communication protocols, like where you do not need any secret key. you just transmit the message directly by encoding it. Then you have quantum dialogue protocol. So it's a duplex version of the QSDC protocol. QSDC is A to B or B to A, but when you use the same channel to do bidirectional communication, then it becomes quantum dialogue. And then there is an extension of that. When you have multi-party version of that, Alice, Bob, Charlie, Dennis, etc., then you have quantum conference, which is like a quantum analog of your Zoom meetings or Google Meet. So multiple people. So there are protocols, and we have also shown some efficient protocols in that domain. So possibly when quantum internet comes, which many people are talking about, many countries people have now, governments have also set up task force for quantum network, quantum internet. So sometime in future, if it comes, so we are assuming that just like in classical, you have these network layers, TCP, IP stuff like the application layer, the transport layer. So in quantum, you'll have similar analogs. Then these quantum communication protocols that we're developing could be plugged in the application layer. Like people can use them when you have the underlying infrastructure to transmit the qubits and efficiently store them and process them. Right? So currently the protocols are at the algorithmic level. Then quantum thermodynamics, okay, that's not my expertise, but there is interestingly one PhD student I got who was from high energy physics background from his master's, and he was very keen to do quantum thermodynamics. So I told him, okay, I will do the quantum information part. So basically there are, these classical thermal cycles, right? There are quantum analogs of that. And when you have quantum analog, the natural question is, how does it affect the efficiency of the heat engine? Right? So whether moving from classical to quantum domain reduces the efficiency or increases the efficiency, or under certain conditions, it can do both. So that kind of things we looked at it from quantum information point of view. Then quantum computing, we have some work. In particular, one of the recent work tries to model errors in quantum computing paradigm. So if you have any quantum computing get set, right? It could be superconducting based platform, it could be other platforms. But if you give the set of gates that are being used there, right? And if you give like the individual characterization of the gates, now if you make general circuits like functions, like build on them, then how you can calculate the overall error, how you can minimize for a particular problem the overall error, so how you can benchmark them. So basically this is statistical and computational work. So that is the work in quantum computing. And also because my background is classical crypto, some of the work in class, and there are some attacks in classical domain, crypto domain, which people are trying to extend in quantum domain. So for symmetric key cryptography, an obvious attack is Grover's attack, which reduces the key size, right? Or for public key cryptography, there is a Shor's attack, stuff like that. But in symmetric recently, there are attacks which are more efficient than the Grover's search, right? So people used to think that for symmetric crypto, at least for non-public crypto, symmetric crypto, is quantum secure, right? So public crypto is quantum insecure, but just like post-quantum crypto, there are specific public key crypto which are quantum secure. On the other hand, the symmetric key, the basic block cipher, stream cipher, for example, the AES, let's say, like these are quantum secure. It's just the Grover search. So you just double the key size and you are safe. There are no other efficient attacks. No quantum algorithms can be used to have more efficient attack, right? It's just the search problem. So given this scenario, recently there are some models where people are trying to combine Grover's algorithm and Simon's algorithm, or Grover's algorithm with other quantum algorithms. And they are showing that if you are allowed to make a quantum superposition query, if the adversary is allowed to make, then actually you have more advantage than Grover. And you can attack with more efficiency, a classical crypto system. But the designing of such an attack depends on the particular crypto protocols, because you have to design certain functions, you have to show certain periodicity of these functions, and then to be able to do the attacks, right? So that is, I would say, design specific. The model is generic, the attack model is generic, that how the adversary should place the query, how the query result should be interpreted, how many queries the attacker can make. how many classical, how many quantum queries. Those things are generic model, but when you try to construct the function to attack, right? So that will depend on the actual algorithm, actual design. So there are some existing attacks we have tried to improve, and also some classical crypto systems for which there are no quantum attacks. There we have tried to apply this kind of hybrid models. So that's kind of quantum computing work.
So when you say you're trying to attack the symmetric crypto system,
right?
And it's going to be protocol specific. So was it AES that you were?
Yeah, AES people have done some work, but the quantum resource that is required is of the order of 1,000 qubits, right?
Yeah,
So to do some simple advantage over the exhaustive search. So that's not practical yet, but yes, even our attacks.
So which one did they look at? I mean, which symmetric one?
So there is some hash functions like HCTR.
Okay.
That kind of stuff we have looked at, hash, especially hash,
Okay.
hash functions. Yeah. So yeah, but yeah, so
AES is
very sophisticated. Yes, yes. People have shown AES attacks, but again, those are very marginal. So in hash functions also we have shown attacks. These are better than AES attacks, but definitely practical implication, not maybe 100, not maybe 1,000, but you need few hundred qubits. So now we are trying to think that, okay, theoretically the attacks are fine, that is well accepted and it is provable. But if you want to verify a scaled down version, like instead of 128-bit cipher, if we have a 16-bit cipher, let's say, right? So then can we verify the attack? So we're trying to think of kind of implementing it, in systems. So that is the kind. So one of the papers we got in ACM transaction on quantum computing recently, this domain.
So do you study the PQC candidates on this?
No, PQC we didn't study. So for PQC, this kind of attacks on works. This model that I'm talking about, they work only on symmetric cipher.
Right.
So they basically improve the Grover's search by adding some more quantum algorithms by combining.
But
So,
I thought there was some hash function.
no, so there are some. So hash functions are not always public. Right? You can have symmetric hash functions also.
Okay.
Yeah. So there are some unkeyed hash functions also, right? It need not be keyed hash all the time. So this basically is many to one.
So do you know if anyone is actually working on quantum safe replacement for AES, or everyone just satisfied with AES, even if it's so complicated?
Yes. Okay. So for public key, people will move to PQC anyway. As the NIST will announce, then people will jump to that. But for symmetric domain, I'm sure AES is going to remain for next 10 years.
Okay.
Definitely. Yeah, there is no substitute. Both from classical and from quantum point of view. There may be some variants of AES. The basic AES structure, there may be some modes like, feedback, like one block gives feedback to other modes. So the modes there are a lot of ciphers people are now coming up, especially in authenticated encryption domain, the Caesar competition. Like the AES they are using as a basic building block, and then they are making a superstructure around AES kind of to make it more secure. And they are showing using proofs that let's say if AES could be attacked with this much parameters, then the original cipher could be attacked with this much parameters, something like that. So and then reduction proof based on the security of AES.
So you don't think people are going to introduce the doubling in size of the AES?
The doubling they will definitely do just to feel safe. I mean, it is like, for example, if you try to buy an apartment, right? So if they say this apartment is going to crash in 50 years and this is going to crash in 1,000 years. So that probably you will not be there in 50 years, but you'll still buy the 1,000-year thing guarantee. So that's just for a psychological perspective. Even elliptic curve system, when is this elliptic curve versus RSA, when people do, so they do the same kind of thing, increase the key size. RSA, like the factoring, with more and more factoring, people just double, like 1024-bit RSA, then 2048-bit RSA and stuff like that. So to me, there is no difference between 1024 and 2048 version of RSA, right? With the current attack, it's just a psychological feel-safe factor. That
Yeah, but AES has been 256 bits for
Yes,
a long time.
exactly. Yeah.
And I couldn't, detect any really serious factors involved with 512 bits. So,
Yes, there's no need. 256 is enough. Probably 128 is not enough because of this grower kind of thing, but because 64 is achievable, right? 2 to the power 64 supercomputer now they can break, but 2 to the power 128 is absolutely fine. 256 bit is absolutely secure. I also agree with you.
okay, that's great.
Yeah.
So thank you. I think we can, we should ask people whether there's questions online. Sure.
Oh,
Please.
Can you go back to the page where you talk something about the second quantization?
Oh, okay. Yeah, representation. Yeah.
So you specifically mentioned that these DoFs are associated with spatial labels. Why do we emphasize spatial? Can't be any other.
Oh, okay. So basically, when you cannot start with indistinguishable particles, right? In practically, if you want to do, or if you want to develop a circuit, you start with distinguishable particles. Then you make them indistinguishable by this particle exchange kind of protocol, correct? So to begin with, you say that, okay, one particle is in location alpha, another particle is in location beta, the spatial location. So they are identical particles, all their degrees of freedom, state, substate, they're all same, except the location, alpha, beta. And then you do particle exchange kind of paradigm. Now it is difficult to say which one is in location alpha, which one is in location beta. So that kind of state is captured in this kind of notation. Yeah. Thank you. It's a important question. Yes.
do we have any questions from the online audience? All right. Do we have any questions from the room?
I have one more question.
Oh, okay, sure.
So, very high level question. Let's say you've been doing some kind of experiment and you just care about one degree of freedom and you ignore all the others.
Yes.
It's still like
For all the particles, you are considering the same degree of freedom, right?
yes, exactly. I'm
Okay.
just looking at one degree of freedom and the other degree of freedom. I never measured them, so they might be maximally depending on I don't know.
Okay.
Are there any implications on what's going on with the degree of freedoms I ignore to the other degree of freedom that I actually care about? Or can I basically treat it as a particle with the same degree of freedom, or particle with the same degree of freedom? I should never measure that. So.
See, for distinguishable particle, there is an effect. So if one degree of freedom is entangled to a certain degree, that will limit the capacity of entanglement in the other degree of freedom, right?
Mm-hmm.
But with that degree of freedom, with maybe the cross degree with other particle, right? But for indistinguishable setting, what this indicates that actually you can have maximal entanglement with multiple particles from the same degree, not only two. So,
Okay, so
that
I have indistinguishable particles I can treat it as a single degree of freedom particles. Because what the other degree of freedom do doesn't affect.
Probably, yeah, when you do the experiment.
Yes.
Yeah.
But if you have single particles, there is some cross degree of freedom.
Right. So no, here one thing is important, that in indistinguishable also the degrees of freedom are distinguishable, right? So you know which one is which degrees of freedom because you are measuring whether the path or the polarization, your measurement device, right? The point is you do not know when you are measuring the path, you are measuring the path of which photon. When you are measuring the polarization, you are measuring the polarization of which one. That you do not. Right. So they are the indistinguishability.
Okay.
So you have to consider both the possibility and a kind of a mixture of that. So that notation captures that thing.
Okay.
Yeah. So that statistical mixture is there hidden in that notation. Okay. So yeah, I think any other question?
I don't think there are any other questions.
If not, then I would like to show a picture of my institute. It's Indian Statistical Institute in east part of India. And probably you know that our city is famous for the birthplace of S.N. Bose, in the Bose-Einstein. S.N. Bose, he was from our city. So anyway, and actually he was associated with our institute also for a long time, for quite some time. So, so we have programs for visitors, also for faculty members, for postdocs and PhD students. We have funds for visits. So if anyone is interested, can approach us, and we will be happy to host you for collaboration for research opportunities. Okay.
Thank you, Goutam.